Hi everyone, welcome to this video on the Comptia Network Plus course, Routing Information Protocol. RIP is a true distance vector routing protocol. It sends the complete routing table out to all active interfaces every 30 seconds. RIP uses only one thing to determine the best way to a remote network, the hop count, and because it has a maximum allowable hop count of 15 by default, a hop count of 16 would be deemed unreachable. This means that although RIP works very well in small networks, it's pretty inefficient on large networks with slow WAN links or on networks populated with a large number of routers. Worse, the dinosaur of protocols had a bad history of creating routing loops which were somewhat kept in check by using things like maximum hop count. This is the reason why routing internet protocol only permits going through 15 routers before it will judge that route to be invalid. If all that isn't nasty enough for you, routing internet protocol also happens to be glacially slow at converging, which can easily cause latency in your network. RIP version 1 uses only classical routing, which means that all devices in the network must use the same subnet mask for each specific address class. This is because our routing internet protocol version 1 doesn't send updates with subnet mask information in tow. RIP version 2 provides something called prefix routing and does send a subnet mask information with the route updates. Doing this is called classless routing. Routing internet protocol version 2. Let's spend a couple of minutes discussing routing internet protocol version 2. We move into the advanced distance vector, also referred to as hybrid Cisco proprietary routing protocol Eigrp. Routing internet protocol version 2 is mostly the same as routing protocol version 1. Both routing internet protocol version 1 and routing internet protocol version 2 are distance vector protocols, which means that each router running routing internet protocol sends its complete routing tables out to all active interfaces at periodic time intervals. Also, the timers and loop avoidance schemes use the same in both routing internet protocol versions. Both routing internet protocol version 1 and routing internet protocol version 2 are configured with classical addressing. Both RIP version 2 is considered classless because subnet information is sent with each route update, and both have the same AD 120. But there are some important differences that make routing internet protocol version 2 more scalable than routing internet protocol version 1, and I've got to add a word of advice here before we move on. I'm not advocating using routing internet protocol of either version in your network, but because routing internet protocol is an open standard, you can use routing internet protocol with any brand of router. You can also use OSPF because OSPF is open standard as well. Table 10.2 discusses the differences between routing internet protocol version 1 and routing internet protocol version 2. Table 10.2 routing protocol version 1 versus routing internet protocol version 2. RIP version 1 distance vector, maximum hop count 15, classical broadcast based, no support for Vlsm, no authentication, no support for discontiguous networks. Routing internet protocol version 2 distance vector, maximum hop count of 15, classless, uses multicast 224.0.0.9, supports Vlsm, allows for MD5 authentication, supports discontiguous networks, covered in network section, Vlsm and discontiguous networks. Routing internet protocol version 2, unlike routing internet protocol version 1, is a classless routing protocol, even though it is configured as classful like Routing Internet Protocol version 1, which means that it sends subnet mask information along with route updates by sending the subnet mask information with updates. Routing Internet Protocol version 2 can support variable length subnet masks, VLSMs, which are described in the next section. In addition, network boundaries are summarized. VLSM and discontiguous networks. VLSMs allow classless routing, which means that the routing protocol sends subnet mask information with the route updates. The reason it's good to do this is to save address space. If we didn't use a routing protocol that supports VLSMs, then every router interface, every PC node, PC printer, server and so on would have to use the same subnet mask. As the name suggests, with VLSMs we can have different subnet masks for different router interfaces. Check out figure 10.4 to see an example of why classful network designs are inefficient. Looking at this figure, you'll notice that we have two routers. Each two LANs are connected together with a LAN serial link in a typical classful network design. Example, Routing Internet Protocol and Routing Internet Protocol version 2 routing protocol. You could subnet a network like this: 192.168.10.0 equals network, 255.255.255.240/28 mask. Our subnets would be, you know this part right, 10, 16, 32, 48, 64, 80 and so on. This allows us to assign 16 subnets to our network. But how many hosts would be available on each network? Well, as you probably know by now, each subnet provides only 14 hosts. This means that with a /28 mask, each LAN can support 14 valid hosts. One LAN requires 25 addresses, so a /28 mask doesn't provide enough addresses for the host in the LAN. Moreover, the point-to-point WAN link also would consume 14 addresses where only 2 are required. It's too bad we can't just nick some valid hosts from that WAN link and give them to our LANs. All hosts and router interfaces have the same subnet mask again. That is called classful routing. And if we want this network to be more efficient, we definitely need to add different masks to each router interface. But there's still another problem. The link between routers will never use more than 2 valid hosts. This wastes valuable IP address space, and it's a big reason I'm talking to you about VLSM networking. Now let's take a look at figure 10.4 and use a classless design, which will become a new network shown in figure 10.5. In the previous example, we wasted address space on LAN, didn't have enough addresses because every router interface and host used the same subnet mask. What would be good is to provide only the needed number of hosts on each router interface, meaning VLSMs. Remember that it is a classful routed network, requires that all subnet masks be the same length. Then it follows that a classless routed network will allow us to use a variable length subnet, VLSMs. So if we use the /30 on our WAN links and the /27, /28 and /29 on our LANs, we get 2 hosts per WAN interface and 30, 14 and 6 per LAN interface. Nice. This makes a huge difference. Not only can we just the right number of hosts on each LAN, we still have room to add more WANs and LANs using the same network. Remember, in order to implement VLSM design on your network, you need to have a routing protocol that sends subnet mask information with the route updates. This would be Routing Internet Protocol version 2, Eigrp or OSPF. Routing Internet Protocol version 1 and Integrated Group Routing Protocol will not work in classless networks and are considered classful routing protocols. Now, what's a discontiguous network? It's one that has two or more subnetworks of a classful network connected together by different classful networks. Figure 10.6 displays a typical discontiguous network. The subnets 172.16.10.0 and 172.16.20.0 are connected together with a 10.3.1.0 network. By default, each router thinks it has only 172.16.0.0 classful network. It's important to understand that discontiguous networks just won't work with Routing Internet Protocol version 1 at all. They won't work by default on Routing Internet Protocol version 2 or Enhanced Interior Gateway Routing Protocol either, but discontiguous networks do work on OSPF networks by default because OSPF does not auto-summarize like Routing Internet Protocol version 2 or Enhanced Interior Gateway Routing Protocol. Eigrp. Enhanced Interior Gateway Routing Protocol is a classless enhanced distance vector protocol that possesses a real edge over an other older Cisco proprietary protocol, Eigrp. That's basically why it's called Enhanced Interior Gateway Routing Protocol. Eigrp uses the concept of an autonomous system to describe the set of contiguous routers that run the same routing protocol and share routing information, but unlike Eigrp, Eigrp includes the subnet mask in its route updates, and as you know, the advertisement of subnet information allows us to use VLSMs when designing our networks. Eigrp is referred to as a hybrid routing protocol because it has characteristics of both distance vector and link state protocols. For example, Eigrp doesn't send link state packets as OSPF does. Instead, it sends traditional distance vector updates containing information about networks, plus the cost of reaching them from the perspective of the advertising route. But Eigrp has link state characteristics as well. It synchronizes routing tables between neighbors as startup and then sends specific updates only when the topology changes occur. This makes Eigrp suitable for very large networks. There are a number of powerful features that make Eigrp a real standout from Routing Internet Protocol and Routing Internet Protocol version 2 and other protocols. The main ones are listed here: support for IP and IP version 6 and some other useless routing protocols via protocol dependent modules, considered classes same as Routing Internet Protocol version 2 and open shortest path first, support for VLSM, classless interdomain routing CIDR, support for summaries and discontiguous networks, efficient neighbor discovery, communication via reliable transport RTP, best path selection via diffusing update algorithm dual. Another great feature of Eigrp is that it's simple to configure and turn on like a distance vector protocol, but it keeps track of more information than distance vector does. It creates and maintains additional tables instead of just one table, as distance vector routing protocols do. To determine the best path to each network, Eigrp uses bandwidth with delay in the line, as well as sending reliability, load and MTU, which means maximum transmission unit, information between routers, but it only uses bandwidth and delay by default. These tables are called the neighbor table, topology table and routing table, as shown in figure 10.7. So as you can see here, in figure 10.7 Eigrp tables, we have neighbor routing table, next hop router, interface, topology table IP, destination 1, successor, feasible successor, routing table IP, destination 1 and successor. So I'm going to leave it here today for this video. If you liked listening, please consider sharing and subscribing. Thank you.